All right, let's go ahead and get started. I want to welcome you back to Unit 12. This is acids and bases, and last time we were talking about a procedure known as a titration, and I want to get back to that. A titration is a technique. It is a procedure for determining the amount of, or I should say the concentration of an unknown acid or base, but it's usually an acid. We're going to say it's an acid, okay? And so what we do is we take that known amount. We know it's volume because we carefully measured the volume using a graduated cylinder, and we placed it into a flask like this one. So say, for example, we have hydrochloric acid. Say it's 30 milliliters of hydrochloric acid, but we just don't know the concentration of it. How do we determine the concentration? Well, we set up this titration, and what we're going to do is we're going to place into this burette. That's the device that you see here. It's a long, slender glass tube called a burette, and it's going to contain your base. The base is going to be a strong base. We're going to say it's sodium hydroxide, and we're further going to say that we know the concentration, okay? We know the concentration of the base in the burette. So we know everything about the burette. We know the base, we know its concentration, and we know how much of the base is going to be required to neutralize the acid. Now remember then that also what was in the flask is an indicator. We're going to use phenolphthalein. We know that phenolphthalein, when it's acidic, when it's in an acidic condition, it's clear, right? It's clear. But if it turns even a slight amount of pink, that's an indication that the solution has turned basic, right? The solution has turned basic. So what we're going to do is we're going to put just a drop or two, no more than that, just a drop or two, that's all we need, of the indicator into the flask. What we're going to do then is we're going to fill completely the burette all the way to the top with a concentrated base like sodium hydroxide, right? And so then what we're going to do is this device right here that is going to control the volume. It's called a stopcock, and it's going to allow us to very carefully control how much drop by drop of the base falls into the acid. So you can imagine as you're releasing base into the acid, it's becoming more and more and more acidic, right? At a certain point, the pH is going to be neutral, and when that happens, that indicator is going to let us know, because it's going to go from a clear color, or I should say clear, to a kind of a pinkish color, okay, to a pinkish color. And so at that moment, you got to watch it carefully. We're going to stop the titration. So maybe it stops right there, okay? And so we're going to measure from here to here. That's how much of a volume of the base was delivered into the flask, okay? And that's going to tell us everything we're going to need to know to determine what the concentration of the acid in this flask is. And we use this formula right here. This is the formula for titrations, and it says this. It says the molarity of the acid times the volume of the acid is equal to the molarity of the base times its volume. So what I'm really looking for then is I'm looking for this one right here. I'm looking for the molarity of the acid, right? I know everything else. So let's take a look at a couple of examples. Let's start with this first one right here. It says 18.6 milliliters of a 5 molar sodium hydroxide solution. It's a base. Solution is needed to titrate 30 milliliters of a hydrochloric acid solution. So let's visualize what we've got here. We've got 30 milliliters of the hydrochloric acid in the flask, right, in the vessel on the bottom. And we have in the burette a base of 5.0 molarity. That's the concentration. In order to titrate, we deliver 18.6 milliliters of the base into the flask. At that point, we stop. Okay, turn the stopcock and make it stop, because the fact of the matter is we have reached neutralization. We have reached titration. The pinkish color has appeared, right? And we'll see that in the laboratory. Probably see it in a couple of videos as well. So that's how much it's going to require. So now let's fill everything into our equation. Remember, the molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base, and it's the molarity of the acid that we're looking for. So let's take a look at how we would manipulate this mathematically. The molarity of the acid is equal to the molarity of the base times its volume divided by the volume of the acid, right? So now what we've got is, let's just plug in. What was the molarity of the base? 5.0 was the molarity of the base. 5.0 molar was the molarity of the base, right? What was the volume of the base? Well, 18.6 milliliters. Do I need to convert that to liters? No. As long as you keep both, as long as it's liters and liters on the acid side and the base side, you're fine. But if it's milliliters and milliliters, that's okay too. You just can't have milliliters for one and then liters for the other, okay? So we'll divide that by 30, and here's what we get. We get 3.1 molar hydrochloric acid. So now we know. Now we know what the concentration is of the hydrochloric acid. It's 3.1 moles per liter. That's what a titration does for you. That's what it accomplishes. It gives you the concentration of the unknown acid by using a concentration of a known base. Okay? All right, let's take a look at example 2. I like example 2 because it has a little bit of a complication in it that I think makes things kind of interesting. Here's what it says. It says, what volume of a 0.65 molar H2SO4 solution is required to neutralize 35 milliliters of a 0.6 molar NH3? Okay? Now, a couple of different things of note. First of all, notice in this case, it is the molarity of the acid that we're the volume of the acid that we're looking for. We're looking for the volume of the acid. Okay? And the acid is the H2SO4. And the base, we know the volume of the base, and we know it's 35 milliliters, and we know its molarity as well. But there's a little trick in this problem. There's a little trick in this problem. And San Antonio students, let me give you a little tip. This is probably going to show up on the test, okay? This is probably going to show up on the exam. So you better listen very carefully right here, okay? All right, here we go. Last time we used hydrochloric acid, right? I want to show you what the dissociation of hydrochloric acid looks like. When you put hydrochloric acid in water, it's going to dissociate into H plus and Cl minus, correct? Which means this, which means that if you have a say for example, let's just say you had a 0.65 molar solution of the hydrochloric acid, you would also have a, stoichiometrically speaking, 0.65 molar solution of the hydrogen ion, right? So you would know the hydrogen ion, right? And this is a strong acid, so it dissociates completely, and that's that. But with the H2SO4, we have a little bit of a caveat, and that's this. H2SO4 dissociates into, it's a strong acid, it's sulfuric acid, but it's going to dissociate into, notice that there's two H's this time, 2H plus SO4 2 minus, okay? That's important. Because what that means is that if the concentration of the H2SO4 is 0.65, then the concentration of the H plus is 0.65 times 2. Okay? Times 2. We have to double it because we have twice as many hydrogen ions as we have H2SO4 in solution. It's a strong acid. So it's going to dissociate completely, right? So what's the difference between HCl and H2SO4? HCl dissociates into the same number of moles of hydrogen ions, but H2SO4 doubles the number of hydrogen ions. You have to take that into account, okay? That's very tricky. Be very careful with that, okay? So let's use our formula. The molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base. That's the titration equation. Now, we want to know the volume of the acid necessary to titrate, but be careful because H plus, remember the neutralization is this. It's H plus OH minus to give you H2O, right? You also get a salt, but we're not going to concern ourselves with the salt, okay? So the point is this. Let me erase this and write this down here so we make it clear. So it becomes H2O, just like that. Still didn't get it quite, but that's all right. The point is this. The point is that we're going to have to take into consideration that the H2SO4 dissociates into two ions, not just one. So here's how we're going to do it. What was the molarity of the base? Well, it was 0.60. See? Base 0.60 molar NH3. What was the volume of the base? 35 milliliters. Put it right there. 35.0 milliliters goes right there. Divided by, what's the molarity of the acid? Be careful here. Be careful because this is the molarity of the H2SO4. But if the molarity of the H2SO4 is 0.65, the molarity of the hydrogen ion concentration is what? 0.65 times 2. You've got to take that into consideration. So on the calculator, when you go do 0.60 times 35, you do this on your own. Don't just take my word for it. Divided by 0.65, divided by 2, because you're going to get twice as many hydrogen ions out of this H2SO4. When we do that, we get 16 milliliters of sulfuric acid is needed to titrate the ammonia, and that'll do it for that problem right there. Okay, don't get caught on that one. Remember, H2SO4 is going to dissociate into 2 different ions. All right, let's move on. Strong acids and bases, what are they? Well, they're strong electrolytes. What does that mean? Well, they break down completely. All right, when you put a strong acid into water, it breaks down completely. And we already looked at a couple of different examples. HCl is a strong acid, okay? It's a strong acid. That means when you combine HCl with water, it just breaks down completely, 100%. H plus and Cl minus. That's what we mean by a strong acid, right? That's what we mean by a strong acid, all right? And then we said that the H plus ions combine with the H2O to form the hydronium ions, right? Now, what about weak acids and weak bases? What are those? Well, those involve something called equilibrium. And what that means is that these acids and bases don't completely break down. They're involved in something called an equilibrium. Acetic acid is a weak acid. It's going to break down into its anion, which is acetate ion and H+. But then those two are going to combine and form acetic acid. And it's going to go back and forth and back and forth. And just like that, it's not going to completely dissociate like the hydrochloric acid did. Okay? So we're going to have another set of rules for dealing with those weak acids, right? Because they don't completely dissociate. That's what a weak acid means. Weak acids don't dissociate. The prototype that I want you to remember for that is acetic acid. Acetic acid is a weak acid. Unlike HCl, H2SO4, those two are strong acids. Okay? All right. So let me ask this question. What is the hydrogen ion concentration of a 0.1 molar HCl solution? Well, remember, hydrochloric acid is a strong acid, so it completely dissociates. So if the hydrochloric acid concentration is 0.10, so is the hydrogen ion concentration, right? Because when HCl dissociates, it dissociates completely, 100% into hydrogen ions and chloride ions. Now, if that's the case, what's the pH? Remember that the pH is equal to minus the logarithm of the hydrogen ion concentration. That's equal to negative, let me do this, log of 1 times 10 to the negative 1. That's what 0.1 is. The power is negative 1, negative 1. The pH would be 1 for that situation, okay? Folks, that's going to do it for this one. I'll see you in the next one. Thanks. Bye-bye.